So yes, today's I'm going to speak about reinforcement learning in robotics. We had a few talks in robotics about robotics, but this is a bit other field, and it's about service robots. Imagine the following situation: you are driving home after a hardworking day, and you are happy to lie in bed, watch some TV or read some book, but then it hits you and you remember, oh, I had a party yesterday and my flat looks like a mess. So I still have to vacuum clean, wash the dishes, etc. Would it not be nice in this situation to have a companion who already did all the work for you while you were working on your regular job? So in my case, the answer is definitely a yes. And this was also my motivation to start the research in mobile robotics. But let's first talk about what are mobile robots. Mobile robots can be different in shape. They can have a very simple shape, like this Roomba we see on the left from iRobot. Many people and many households have this robot already. And it's a very good product and it does its work. But also mobile robots can be way more complex, like we see on the right. This is a humanoid with a wheeled base from Pile Robotics. The model calls ARI or ARI. And this is way more complex system than the Roomba. It has way more degrees of freedom. So they're completely different. But let's now discuss what mobile robots have in common. So all robots have sensors, and they try to perceive the surroundings via the sensors. And based on what they see and what they record, they need to adapt to changes in their environment. So it's not a repeating work. It just react based on sensors information. And the main capability of mobile robots is autonomous navigation. What is autonomous navigation? To speak simply, it's just reaching a goal location in the environment without any human intervention. And of course, over the years from the 90s till now, people work on that, and this task can be considered solved in the research. And a lot of approaches use a two-step approach. And in the first step, they perform motion planning. And in the second step, motion execution. And this maybe seems a bit abstract. Let's discuss this a bit detailed. Here we see a navigation scheme. A lot of modern navigation systems in robotics have this structure. And let me break it down here. So before we start our navigation, we have the environment mapped out. Usually you do it beforehand, you do a mapping run, record all the obstacles. And when you start your navigation, you have to rely on your sensors in order to localize the robot. So the robot has to know where it is. And when this is done, the robot gets a target goal where it has to navigate. And first, it goes into planning. For planning, we use a grid map. Basically, we're laying a grid over the environment, and all the obstacles are black and all the free space is white. And we can do a graph search on this map via A* or similar algorithms, and then we get a collision-free path. Because this takes so long, usually these planning modules work in low frequency. So let's say once in a second with a frequency of 1 Hertz or even 0.1 Hertz and so on. So after we get the collision-free path, we subtract a sub-goal from this path. Usually this is, you use a combination, a distance to the robot and the path itself. So you basically define the sub-goal, the point on the path that is 1 meter away from the robot. And then you give it to the execution module, and the execution module has the function to avoid collisions. because unexpected things happen in the real world. So people can run through the robot paths, environment could be changed, we can close doors. So this module have to react to changes in the environment. So we have like a global plan, but what's going on right in the moment, this is what is handled by the execution module. And obviously this has to work with high frequency. We're talking about 10 Hertz here. And yes, the purpose is to avoid collisions. And this execution module computes or determines the motion commands, which is the linear and angular velocity v and omega, and send it to the robot. And then these commands are applied to the robot for a short period of time. We're talking about 0.1 seconds. And then this loop repeats again. And so on while the robot is driving, till we reach the goal. So this is basically the basic navigation scheme. And I told already about the planning. The planning is performed with a star search on a graph. That is a map. And for execution modules, there are also several solutions. And one dominant one is, or state-of-the-art solution, is the dynamic window approach. And the goal here is obviously to sample the control commands v and omega to the robot. But how it's done? Basically, we have a set of velocity commands that we can apply to the robot. And for every command in the set, we try to predict the outcome for a short period of time into the future. And basically, what predicting means here is we compute the trajectory that the robot would take if he would choose these commands. And then we have an objective function and use this to evaluate every trajectory that we computed. And the best one we choose and send the velocity commands to the robot. And then repeat this step again. And this works very well, it's reliable and well understood and not so complicated. So it's very wide used in robotics. So then you might ask, okay, when the task is solved, what you're doing here with your presentation and why do we need reinforcement learning for that, right? So there is one problem when operating the systems is there are a huge amount of parameters. And in order to have the system running appropriately, like without collisions, very fast, you have to tune it. And this takes a lot of time and know-how. So basically, you have to know the robot, you have to know what kind of environment you're operating and stuff like that. And even if we talk about future systems that are delivered to customers, you would want that the robot, when it comes home, give the robot 1 week, it will learn everything, learn the environment by itself. And after 1 week, self-learning, it can operate in the environment. This is the future of the product that I have in mind. So all these things can be achieved with reinforcement learning. Okay, this is a future vision, but let's break the current goal that we had with this research, or let's define it more clearly. So the goal of our reinforcement learning here is to determine the velocity commands for each time step to navigate collision-free and as fast as possible to the goal in real time. Real time is very important here because, like I said, this module works with high frequency, this collision avoidance module. So we can't have a machine learning technique that takes several seconds. Even 1 second would be too much. Okay, and this is how we solve it. This is the overview of our approach. And I will discuss every point here in detail in the next slides, but here a quick overview. So for our approach, we use the local map around the robot, that is 3 times 3 meters. Sub-goals that we extract from global paths, I will explain it later again. And the current velocities of the robot. It's basically the angular and the linear velocity. And this data we feed into the network. And after training, we expect it to give us the best motion commands for the next time step. Okay. This might here in the step be a little confusing. Let's break it down. So first, what algorithm did we use? This is a proximal policy optimization, and this is, has an actor-critic design, this algorithm, and whereby the actor and critic are represented by a deep neural network. And one of the main advantages of this algorithm is that it reduces the vulnerability to high variance rewards. And this was key in our case, in our study. So how we designed the system. First, the input to the network. What we do provide with that. I already told that we use the linear and angular robot velocities, but now how do we extract the subgoals? So when the robot is driving, we always save the current subgoal that is 1 meter away from the robot, saves this in the memory. And when we continue our run, and we are at the moment at time step t, we use the previous local goals that we saved in memory for the input for the neural networks. These are 4 values, x and y coordinates for every subgoal, and we use the subgoal. If we are in time steps t, we use the subgoal t-1 and the subgoal that we recorded in t-5. Okay, the other part of the input differs in structure. It's an image of the occupancy map. Like I said again, here we see on the top images, the robot is driving around obstacles. And you see in this light blue color is a cropped image around the robot. And this is what we basically feed to the network. Of course, we rotate this rectangle such the robot is in the middle and always looking to the right. You can see that on the second row here. And yes, again, this is an occupancy grid map, so it's a binary map, and the patch is 3 times 3 meter big. So with a resolution of 5 centimeters, we have an image that is 60 times 60 pixels. Okay, this is the input to the network. Now the end output is pretty much obvious. Linear and angular velocities, that's what we want to get from our policy, from our net policy estimator, the network. And of course, because we have to deal with physical systems, we have to crop the velocity space. And in the linear direction, we crop the velocity from 0 to 0.7 meters per second. This means that the robot can only drive forward. We're doing this for safety because a lot of simple robots do not have sensors at the back, so it's very unsafe to drive backwards. And for the angular velocities, we crop the velocity to 0.7 radian per second in both directions, so to the left and to the right. Some technical details here. Okay, how we defined our reward functions. This has 3 components, this function. And the first one is the final reward, our fin. And it's a large positive value if we reach our final goal, basically if we were successful. And the large negative value if the robot collides. So basically, that's not a success. And 0 otherwise, so every time step. So this is the final reward at the end of every episode. Our fix is a fixed negative reward that penalizes each action, and that forces the robot to finish an episode as fast as possible because we give a negative reward every time step. So the lesser time steps, the bigger the final reward. And the final component scales with the distance, so our dist, to the previous subgoal. And this reward speeds up the training and encourages goal-oriented navigation behavior. So this reward component helps us a lot in order to find the right policy. Okay, this is our neural network structure. So I said we have before already we have an input that has two different data structures. So it was also very clear that we have to use two branches in a network in order to process this two different data structures. So the first are the scalar values, as in the first are the data structure is the scalar values, and we process it via fully connected layers. And the second one is an image, binary image, and we use for that several CNN layers, and at the end we concatenate it and dense it up a bit. And so for the critic output, we estimate, with a single output, we estimate the value function, and the actor output two mean values and two standard deviation values of two normal distributions. These are basically these two distributions that represent the velocities. And then we take this distribution and sample from this the velocity. So this is how we do it. Okay, this was the theory and the background and development of our approach. Now we are coming to the training and evaluation. So for the interested audience here, the short note about the implementation. We did it in ROS, the robot operating system. For communication, the simulated environment we did with Gazebo, and all the reinforcement learning and training stuff we did with TensorFlow. And we trained, I think overall, over 1 million episodes in environment 1. We see it on the right here as a 10 times 10 meter environment. Again, black is here the obstacle in the middle, and white is free space. And for training, we randomly choose a start and goal position. Yes, and each episode was limited to 1,000 steps. Our controller run with 10 hertz, and the overall training time took about 24 hours. This was the training, and now the evaluation. So our plan at the beginning was that that our approach should require as less training as possible. So our plan was at the beginning to train only in environment 1 and to test it in 6 environments. So the testing environment and then more complex environments. So again, we see here white free space, black occupied. The second environment, environment 2, is the same as 1, but longer with a second obstacle. Environment 3 has a slalom track that allows like for fast movements or dynamic movements on the 2D plane. And the third environment, environment 4, or the fourth environment, has obstacles that has a round shape. And this was never experienced by the network. So we wanted to see the generalization capabilities with this map. And environment 5 and 6, I talk about this in more detail, but these are very chaotic maps with a lot of narrow spaces and also round obstacles. And yeah, I will talk about in a few slides, I will talk about these maps. So the evaluation was done regarding 2 points. First, the success rate, this meaning how often do we reach the goal, and the completion time, how fast did we reach the goal, right? Let's first discuss the success rate. So for the evaluation, we performed 400 runs with equal start and goal settings on each environment. And of course, the dynamic window approach managed to reach all goals in all environments. So success rate was everywhere 100%. Our approach had almost the same results through environment 1 to 4. And I think in environment 3 and 4, it had, I think, 1 collision. But the performance decreases drastically in environment 5 and 6. So environment 5 is okay, and environment 6 is, well, not so good. And so we investigated the fact, investigated the fact why we're performing so bad, and we discovered that one fact that the robot wasn't able to learn in environment 1. And I will go back to basic navigation in robotics. So what we do is robot has a radius, but when we do planning, we reduce the robot to a dot mass. And in order to still generate collision-free paths, we need to inflate instead the obstacles. And this has the advantage that we only have to check one cell for collisions instead of every cell in the robot radius. It would take a much longer. So, and the standard approaches without reinforcement learning apply all this inflation. So they reduce the robot footprint to a dot mass, but inflate the obstacle. And if it's a narrow path, this path can be closed through the inflation because we basically make the obstacle bigger. Because we don't use it, it happens that a path leads through a narrow passages where the robot doesn't fit. So the robot has to leave the path, circumvent the obstacle, and go back to the path. This is what the robot needs to learn and wasn't able in environment 1. So we try to improve the performance by let it train again for 8,000 episodes only on environment 6, where this situation appear the most. And this is how the performance improved after only 8,000 episodes further training episodes. So environment 5, we reached always the goal, and it was a 25% improvement in comparison to the results of the first training. And environment 6, we almost reached the goal in 85%, and this was a 26% improvement. Okay, here we see an in detail analysis. So on the left, we see this the Gauss map here. Basically, it's here on the right. It's more 3D illustration, and then we see here a 2D map. And on the left, in red, shown the collision that appeared through the 400 runs after the first training. And this on the right, still the collisions in red, but after the second training, we could reduce the collision significantly. The most collision appear here in very narrow spaces, and to find out why exactly every collision needs more investigation. Okay, so this was the success rate, and now we are talking about the completion time. So for every success run, we took the time from the dynamic window approach and the reinforcement learning approach and recorded the time. And it turns out we are faster than the classical dynamic window approach, especially in environment 5, where you can save a lot of time by having a dynamic racing curve instead of a typical old approach that we see here in the next slide. You see here on the red, this is environment 3, and on the right side, you see in red the trajectories of the almost 400 runs of the dynamic window approach. And you see here around the black obstacle, it's more like a wider curve that the robot always takes. And this exactly is the effect of the inflation, because it makes the obstacle bigger and the robot has to drive around. While our approach doesn't use any inflation and has to find out through trial and error what's the optimal distance in every situation. So he can save here and there and have save some room and here and there and have a dynamic curve while navigating. And this is the reason why it saves time. I would just want to say that the dynamic window approach needs to inflate the obstacle. It's not just an option, but this is like a technical trick in order to make this approach work. So, like I said, because we are using dynamic curves, we can save time and it's not only the space that it's not only the cutting corners, but we are also able to have constant high linear speed, and that's why we're moving faster to the goal. Okay. So, and the last point that I want to talk about is the real-world experiment. It's very important in robotics because we trained in simulation, and in real world, in robotics, real world and simulation robotics are two different worlds, let's say it this way. Because we have much more errors in the real world. We have localization errors, sensors that do not work perfectly. We have light conditions. The robot is bumpy a bit when driving on the floor, it's shaking. So all these errors, they can add up such that an approach that worked in simulation is not working in real world. So this is a very important experiment. And yeah, the good news is the approach worked without any adaptation. So we took it from simulation and performed it here on this experiment. On the left, we see our lab mapped out, or part of our map. And the robot has to get from start to the goal. The start is in corridor. It has to pass the door, pass the obstacle in the middle, and get to the goal in the corner. And we performed for the dynamic window and our approach this experiment 10 times. And we were about 10% faster, about 3 seconds faster than the dynamic window. So the results here also gives us a good feeling about it. We can use it indeed on the real robot. So the results on the real world is still we are faster and always reaching the goal. Basically the same as it was in simulation. Okay, let me quick conclude this work. So we proposed a new approach to learn a navigation policy for a mobile robot. We use modern reinforcement learning approach called the proximal policy optimization. We wanted to train a network that choose robots' linear and angular velocity commands for the next time step. And our input was the robot velocities, the local goals, and the local map around the robot. The training was simple in a simple environment and was applied to further complex environments. The policy learned to reach the goal, and the benefit of this approach is that it has smooth trajectories without any tuning. So we simply let it run and then applied it, and it has all figured out, all the distances. No tuning would be needed, but simply the training was enough. And this was the goal at the beginning, and this is what we achieved. And also, we are faster than the classical dynamic window approach, about 16%, and we can apply it to real world scenarios without any adaptation. So I'm finished. Thank you very much.